we're going to sketch an actual curve. Now in your book you have some like a template that I made of curve sketching recipes, like step by step you follow them. On tests, you're not always going to have every single step laid out for you like that. So that gives you a tool to help you remember what exactly you're supposed to find every single time. Okay, so let's sketch this curve. First things first, we look for discontinuities. We look for the domain. Are there any domain restrictions on this function? No, because there's nowhere where I would divide by 0, and there's nowhere where I would take the square root of a negative number. Therefore, there are no domain restrictions. So my domain is all real numbers. So what does that tell you? You're like, okay, so I know the domain's all real numbers. What now? That means there's no asymptotes or holes. Okay, so we don't have to graph any of those, and we don't have to look for those. Okay. The next thing we want to look for is the Y-intercept. The Y-intercept is the easiest intercept to find. All you do is you plug in 0 for x, and you solve. And this one's really easy because I plug in 0, and I plug in 0 here, and I plug in 0 here, and you notice that 0 times who cares what's inside of here is always going to be 0. So my Y-intercept is 0, 0. What about my X-intercept? X-intercept's a little trickier. I have to set y equal to 0 and then solve for the x values that create that. Okay? Well, remember, when I have something factored like this equal to 0, I just set each one of the factors equal to 0. So I say x equals 0, x minus 1 equals 0, x plus 2 equals 0. All right, so I have either x equals 0, x equals 1, or x equals negative 2. Those are my three options. Those are my three intercepts. Okay, and we can tell if those are odd or even. Remember, odd intercepts go straight through or wiggle if they're a third, right? And even ones bounce. So 0 is odd. 1 is odd, and negative 2 is even, because the factors that created each of these zeros are odd, odd, even. Okay, so straight through, bounce. Now we're going to look at end behavior. Now the first thing you think of in calculus with end behavior is, does it have a horizontal asymptote? Very first thing we think about. This is a polynomial. Polynomials don't have any fractions or radicals or anything crazy like that. There are no horizontal asymptotes. Because think about, a horizontal asymptote says the limit as x approaches infinity. What's happening? Well, when x gets really big, we just get big numbers times big numbers times big numbers. So we just get big, huge numbers, right? So we can say, what's the end behavior? Well, this would be a big number, and that would be another big number, and that would be another big number. So it's going to go, when x approaches infinity, it's going to be going up like that. And what happens when I put a big negative number in here? I have a negative number times a big negative number, okay? A negative number times a negative number. This one's going to be positive because it's a big number squared. So the limit as x approaches negative infinity is also positive, so it goes like this. And if you remember way back to pre-calculus, when we learned about this, this is that odd and even end behavior that's been kind of like peskily like picking at you because you're thinking of symmetry and end behavior and trying to like think of them the same way. Okay, symmetry, odd and even, is different. This is end behavior. So what's happening to this function as x gets really, really big? Well, it has an even degree, see, because x times x times x squared would be x to the fourth. So this is an x to the fourth is the main piece. So remember, x to the fourth is even, therefore its end behavior is even. That's why it's either going to go like this or it's going to go like this, and because we just checked to see, well, it goes up. When x gets really, really big, it gets really, really big, positive. We know that it goes up like that. All right, let's see if we can graph it. So we have an intercept at 0, an intercept at negative 2 that bounces, and then an intercept at 1 that goes straight through. And we know we start up here, we bounce, we go through, and we come back up. And really, like polynomials, remember, these ones actually made a lot of sense. You know, this is a quartic, It looks like a quartic. Awesome. Okay, let's look at a slightly more challenging one. Okay, domain of this one. So again, domain is where would I have restrictions? What are numbers I can't put in here? Well, I can't put 0 because it would cause 0 in the denominator. I can't put 1, and I can't put 3. All of those would cause a 0 in the denominator, and they are not okay. Now, do you see this g reduced of x? That means we're going to go ahead and cancel out things that are similar, and we can write a reduced function. That's what red stands for. So when you see that on the test, don't freak out. Don't raise your hand and say, Ms. Marie, I don't know what that means. I'll probably still answer your question, but I might roll my eyes a little bit. Okay, so let's cancel out things that are the same. There, 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 and those are not the same. So what do I have left? I have x minus 1 times x plus 3 cubed on top over x times x minus 3 squared on bottom. Okay, so which ones are wholes and which ones are asymptotes? Well, what's still left? 0 is still a problem and 3 is still a problem. Therefore, those are vertical asymptotes. If they are still there after we reduce, they are a vertical asymptote. Then what is no longer there that was there before? Well, 1, right? X equals 1 was there but isn't anymore. So we have a hole at x equals 1, but we need to find the rest of the hole. We have to find the other part of the hole. So we have to plug 1 back into the reduced function. And this one gets easy too, because if I plug 1 into here, 1 minus 1 is 0, times 4 cubed over 1. None of this matters because 0 times anything is 0, and then 0 divided by anything is 0. So my hole is at 1, 0. Now let's look for x-intercepts. Remember, x-intercepts are where y equals 0. So I set y equal to 0. We'll alternate colors so it's a little easier to tell. We set y equal to 0. And if you remember, oh, that was huge. The bottom can never equal 0, right? Because that's a problem in the domain. So how do we find this? We just set the top equal to 0. We say, when does this factor equal to 0? And when is this factor equal to 0? And those are the two things that would make this equal to 0, the whole function. Okay, so when is y equal to 0? When x equals 1 and x equals negative 3. Either one of those places, y is equal to 0. Because if I put them in, I would get a 0 on top. But wait, there's more. Can both of these be our x-intercept? Nope. Because look, I have a hole at 1, 0. So I can't have an intercept at 1, 0. Like, I'm going to go really close, and then I'm going to have the hole, and then I'm going to keep going. But this is kind of one of those false things where it tells you, the algebra tells you there's an intercept there, but if there's a hole there, it can't be an intercept. Okay? So our only intercept is at x equals negative 3, and it's going to be an odd intercept because it has an odd power, and it's going to do the loop, that thing. Because it's a cubic, right? This is cubed. So instead of going straight through, instead of bouncing, it's going to look like the cubic function when it goes through. It kind of flattens out. Okay. Y-intercept. We set x equal to 0, and we solve for y. So I'll do the work down here. I have 0 minus 1, 0 plus 3 cubed over 0 x minus 3 squared. All right. What's the problem here? You're like, oh man, can't one just be straightforward? No. Nope, sure can't. What's the problem? 0 can't be in the denominator, right? And if 0 is in the denominator, then we have an asymptote. So can we have a y-intercept? Do we have a y-intercept? No, because we have an asymptote at 0. So it never actually crosses the y-axis, okay? So none. And let's look at our end behavior. Okay, so let's look at the function, the degree of the function. Oh, this is not a polynomial, so we'll actually look at the horizontal asymptotes and see what's going on. Remember, end behavior means the limit as x approaches infinity and the limit as x approaches negative infinity. That's all end behavior means. And last year we did it without using those exact words, but it's still the same thing. What happens when x gets really, really, really big? Okay? Now let's look at our function. We have an x to the fourth on the top, and we have an x cubed on bottom. And remember, we don't care about anything else because all those little things don't matter. When you put one Google into this, none of the little stuff matters, okay? So, what's going on? When x to the fourth over x to the third, that's the same as just x, right? If that simplifies down to x. What happens when I put a really big number into x? I get a really big number out, don't I? I put in a huge number, I get out a huge number. I put in a huge number, get out a huge number. That's it. It's that simple. If you put in a huge number, you get out a huge number. If I put in a huge negative number, I get out a huge negative number. So the limit as x approaches infinity of this function is infinity. And as it approaches negative infinity, it's negative infinity. So my end behavior is going to be like this and like this. Okay? Now let's sketch it. Whew! There's a lot. So we start with our vertical asymptotes. Sketch each of our vertical asymptotes. We have one at 0, and we have one at 3. We have a hole at 1, 0. We have an x-intercept at -3 that is like a cubic intercept. And we don't have a y-intercept. And we know the end behavior. Okay, well, let's do this. So we know that it starts way down here, right? So I can come here with this. Let's do this a different color. Okay, so it comes through and then approaches that, and that should be like kind of flattened out because it's a cubic. Okay, and then what happens over here? Well, it has to go up like that, but it can't come down, can it? No, because there's no more x-intercepts. We know, we found all the x-intercepts, none of them exist over here. It can't come down. It has to stay up. So we know that this has to like go like this. It has to just come down a little bit. Again, we don't know with calculus yet how to find that, how far it comes down, but we know it comes down, but we know it absolutely doesn't touch the x-axis. Okay, now what do we do in the middle? Well, remember, we can find if an asymptote is even or odd. So let's go to our asymptotes. We should have written whether they were even or odd. 0, is that an even or odd asymptote? I go back to the power that created it, the power of the factor that created it, and I see that it's an odd power. So this is an odd asymptote. And I see that the power of the factor that created this one is even. So this is an even asymptote. Which means, since this one is an odd asymptote at 0, since this one's going up, this one has to be going down. So I'm going to go that way. All right. And then this one is an even asymptote. And since this one's going up, this one also has to be going up because it's an even asymptote. So it skips the hole and goes like that. And then we're done. That's our sketch. I know it's a lot. It's really intense. You have to truly understand what holes are, what asymptotes are. But the more you practice it, the better you'll get.